infinitesimal. Okay, it is not infinite small. Okay, it's a separate word, which is I think accepted by most dictionaries. Okay, and so I spent about I think 15 minutes yesterday, changing all infinite smalls into infinitesimals. Okay, so anyway. Okay, so we did finite screws. So now we'll look at infinitesimal screws, and so they are also called instantaneous screws. Okay, and it started with people starting to study unique descriptions of motion and forces on a rigid body. Okay, so the problem was that if you take a point has a velocity, right? A point has no angular velocity. So that was the earlier approach, and Newton's laws are applicable to a point or a particle. Then people evolved the concept of a rigid body, right, where the distance between points is invariant. So if you take 3 points and you say distance between them invariant, then their relative locations do not change in space. And you move forward, and they tried to write or describe the mathematics of that, and it was not easy. So there are bunch of people struggling over a century. So and so there is Giulio Mozzi, obviously Italian, right? 1738, between 1813, then Casals and Poinsot, they are French, and R.S. Ball, who is Irish. Okay, so by the time R.S. Ball came around, he basically put the thing in complete shape. So we had a description of kinematics of rigid bodies and dynamics of rigid bodies done formally in a mathematical form. The book I studied from is this K.H. Hunt Kinematic Geometry of Mechanisms, and actually the screw theory course was taught by Professor Hunt when he came around to Ohio State University. So now this R.S. Ball's book has recently been republished, and there is a copy in the library, but it is slightly difficult to read. The Hunt's book is clearer, and it also contains a lot more of planar kinematics, so you can read it. It's a readable book. So then you can go and you can find out who is this and who is this. Okay, these are very interesting people. Well, obviously one of the 4 people mentioned there. Okay. These are there in Wikipedia, so you'll read up more on them. They have tremendous contribution, including Casals. Okay, tremendous contribution to mathematics. All of them, in fact. Have you heard about? You must have heard about Casals before, right? No. Huh? Oh, yeah, earlier lecture. Other than that, in some other course? Huh? What did you do in 110? What did you do?
We studied its theorem about the 3-dimensional motion, which can be represented as sum of translations and rotation.
Achha, sum of translation and rotation. But they didn't tell you it's about the same axis? No? Oh, that's a loss. But anyway, so he had more. He lived very long, and he had tremendous contribution. Anyway, so now coming back to line in the plane. So you take a point somewhere here, take a point 2 somewhere here, right, and then you say, okay, I have a line going from 1 to 2. Okay, so this is a directed line. And you call the component in the x direction, I am calling it L. Okay, so it's very simply equal to x2 minus x1, which can be represented through this determinant. Okay. If you take the component in the y direction, that is y2 minus y1, that can be represented by this determinant. This is just a representation. Okay. Now, so this gives you essentially, if you have these two components L and M, it gives you two kind of like direction cosines. You still have not normalized it. It gives you two components, x direction component and y direction component. Now these two components, so hence determine a direction of a line. So you can have a line here, you can have a line here, you can have another line here, and they will all have the same components. Now as you draw these lines, they move further and further away from the origin. So that is the only parameter which basically quantifies the set of lines which are parallel to each other. Okay. Now we are just talking about plane. We will get on to 3D later. So the next question is, you talk about moment of a line. So you are talking about the moment of a unit force applied along the line about the origin O. So it is F cross A. And now I will just flick back here. I should have reproduced this picture there. Now when I define this, so my F is going here cross A. Now I want to define the moment to be positive about the z axis. So my A has to be defined from the line to the point, right. So it is not the classical way of doing it, or the commonest way of doing it would be to draw a line from O to the line, is the other way around. Is drawn from the normal from the line to the point. Okay. So then you get a positive z value for a line which is going there, which is what you want to do. Okay. I am pointing this out because normally when you find a velocity, you also do a omega cross r kind of thing, right. But that r goes from the origin to the point of interest. So it's reversed out. Keep it in mind. So you can break this down, and you can want to represent the moment by r, capital R. So you can then compute this. I'm sorry, I should have put this picture there. But anyway, so if you take x1, y1, so here is the point, and then you can multiply it by L and M, x1 into M minus y1 into L, which is the moment about the x axis, z axis. So you can represent it as this determinant, and this turns out to be this determinant x1, y1, x2, y2. Okay, after simplifications. So finally, if I now look at this matrix, which is 1 x1, y1, 1 x2, y2. So from this I can form three determinants. One is 1 1 x1 x2, which gives me L. I can form 1 y1 1 y2, which gives me L, and then if I take x1 y1 x2 y2, I get R. Okay. So these L, M and R, they are the coordinates of a line in the plane. Okay. So now what have I achieved? Because if you want to define a line in the plane, the commonest form that you are familiar with is y is equal to mx plus c, right. How many parameters are there? Just two parameters. In this description that I am now giving you, there are three parameters. It's a stupid thing to do, right. But y is equal to mx plus c was known before. So why am I interested in doing this? Okay. Now that's a question which should come to you, right. If it hasn't come to you, you are not thinking. Okay. We will not answer the question now, we will answer the question later. So I want to extend it to 3D. So it's very simple, it is 1 x1 y1 z1, 1 x2 y2 z2. How many determinants can I form now? 6, right. How do you get 6? for C2. So you can form 6 of them. So there are 6 parameters. So we already seen L, M and R. So we define N, P and Q. Okay. And so you define N like this, and then Q, and then P. And this is an interesting definition. So here you are not using 2 points. So this one uses 2 points, right? Z1 x1, Z2 x2. But this one is Zx and L. So you need only 1 point on the line and just these 2 parameters to define Q. Okay. And similarly here, Y, Z, M and N. Okay. So this gives you a 6 parameter definition of a line in space. What is the equation? The earlier equation you knew of a line in space?
X y plus y is equal to y by b is equal to z by c is equal to constant.
Plus D equal to 0. How many parameters? 4. Here we have 6 parameters. Not good. So we will see what happens. And so we are looking at this second set of definitions. So for any point x, y, z on the line, instead of specific points on the line, and so we write this as typically coordinates as L, M, N, and then we put a semicolon and write P, Q and R, because there are different kinds. This L, M and N are essentially direction cosine like things for the line, and then the P, Q and R, they are the moment of a unit force acting along the line about the origin. Okay, so you put in semicolons. So now these are called so when you have 2 sets like this, so this is a vector L, M and N, and then this is another vector which is the moment of a point. So this is 2 vectors, each is a, so when you have vector with 3 components, what do you call it? Vector with 3 components? You know these nomenclature, tuple, triple, no. This is the problem with days of objective type questions. Anyway, so this has 2 vectors, each is of dimension 3. Okay. Anyway, and this system is from Julius Plucker, and so who was again a very famous German mathematician. Okay, and amongst his more famous students was Klein. You heard about Klein? No. Klein's bottle. Klein's bottle. Have you seen one? No. Should go back and wiki it, right? So these are things you should know when you're graduating from IIT, right?
He was a geometer.
You were a geometer. So was this guy. Everybody, those days everybody was a geometer. The last great guy was Gauss, I told you. He was called the last complete mathematician. After that, mathematics became so big that you could only specialize in either analysis or in algebra or in something or the other, right? Or in topology. You did not know all of mathematics. So, and he has outstanding other contributions, including how to classify curves. So they are called the Plucker equations. So anyway, now let's work on that a little more. So there is this thing called, we note, so you have the vectors L, M and N, and then you have the vectors P, Q and R. Now these are by definition they are perpendicular to each other, because one has been obtained as a cross product. So you got PQR as a cross product of L, M and N with A, right? Since you obtained it as a cross product, then PQR has to be orthogonal to L, M and N, right? So if you take the dot product, you will get 0. So LP plus MQ plus NR is equal to 0. That means if you know 5 of them, you can find the 6th term. Okay, and this relationship is called the quadratic identity. it has got more implications, but we'll just call it the quadratic identity, or it's written as Qi. So we essentially say, okay, now we don't need 6 coordinates. The second thing is that only the ratios are important, because which point x1, which point x2 really doesn't matter as long as there are 2 points in a line, right. So if you take points which are further away, then your L, M and N will scale, and correspondingly, even if you are the same distance say away from the origin, your PQR will scale by the same amount. So it's only the ratios which are important. So what you write is usually a ratios of L is to M is to N is to P is to Q is to R. Okay, the individual values are not important. This plus if you use a quadratic identity. So essentially you are back down to 4 parameters, which is what you are more familiar with. So this is not a redundant or a very bad description of line in a space. It's the same parameter space that we are talking about. And so there are 4 infinity of lines in space. Okay, you are familiar with infinities, right? 1 infinity, 2 infinity. No? Come on. How many points on a line? Infinity. How many points in a plane? 2 infinity, right? There has to definitely more points on a plane than on a line, isn't it? Definitely. So how many lines in a plane? 2 infinity, right? 2 infinity of lines in a space. So, but infinity is really bad, right? People didn't like infinities those days. In fact, even now it's not understood very well. So and so this is where this thing comes in handy. So you start with this, they take the plane z is equal to 0. So you could take any plane and you could do coordinate transformation and rewrite it, but for simplicity we will start with the plane z is equal to 0. So you take Tx plus Uy plus S is equal to 0, where x and y are the points on the plane. So how many of them? So that this defines the full plane. So what we then do is we scale x and y, we divide by w. Okay, I can do scaling because I have this plane here. I can draw a coordinate system and I say, okay, now all these points I describe in that coordinate system. I can just change the scale of the coordinate system. I still have the same plane. So any point which I had earlier, I will rescale, right? So I get this formula. So now from this, if I just multiply it by w, I get this form Tx plus Uy plus Sw equal to 0. Now this is called homogeneous because all of them have 2 terms. This was not homogeneous. This had 2 terms, this had a single term. Okay. So this was a funny equation, this is a regular equation. So all your life you have learned the funny equation, but not the regular equation. So this regular equation you have to wait for people like Points and Mosey to figure it out. Now we ask this question that how do you get a line at infinity? So I have a plane, right? So there has to be lines at infinity. So either x is equal to infinity or y is equal to infinity, right? Or both are equal to infinity. So it's a big problem. So how do you write it? Now if I write x equal to infinity, then I'll be in trouble, right? I cannot work with this equation at all. Everything else vanishes in that equation. On the other hand, if you look at this equation, you can make x go to infinity by making w go to 0. If I make w go to 0, I am still left with Tx plus Uy equal to 0. So I still retain some parameterization of the space, of the plane. Okay. So it does not become that I cannot work with that equation, that is number 1. Number 2 is that, see, you have all these problems with infinity, 1 infinity, 2 infinity, 3 infinity, you cannot multiply, divide very nicely with infinities, but 0 is much better known than infinity. You just have to be careful you don't divide with 0. Otherwise you can add with 0, multiply with 0, subtract with 0, at least you can do 3 operations. With infinity you cannot do anything, you know. A number plus infinity, yes, it is infinity, but is it more infinity, less infinity, right? and multiplying to infinity is obviously much more difficult task. The 0 only problem is just don't divide by it, everything else is fine. So similarly, we take the equation for plane in 3D homogeneous coordinates, and it becomes Tx plus Uy plus Vz plus Sw equal to 0. Okay, so everything has two terms, and you get equation of the plane in homogeneous coordinates. So we take that equation, and this represents all points x, y, z, w in a given plane T, U, V, S. Okay, so this is a general plane, so 3 parameters, or it represents all planes T, U, V, S passing through a given point x, y, z, w. Okay. And so these are the same equation represent two things. Okay. So this is what is called geometric duality or geometric incidence. Okay. And so similarly, the join of 2 points, intersection of 2 planes concept that we keep talking about for the line. So we are talking about plane and a line. So similarly, if we take 2 points, you can again define a line, and then that is again geometric duality or incidence. So if you get w equal to 0, it implies that you have a plane at infinity in this. So you get points at infinity and planes at infinity all coming through that, and then you can multiply out by a constant non-zero scalar and end up in the same plane. So there is no change in the plane. So if the definition of the plane is the same, then just multiply by any constant scalar, it does not make a difference, you are still in the same plane. Now here is the interesting thing, if it does not make a difference, then what you do is, that is why you keep w by definition as equal to 1 unless you want the point at infinity. Okay. And that is why when we are doing this so called homogeneous transformation, we always had x, y, z 1 sitting in there, so that 1, right, comes out of this homogeneous coordinate set, and that is why they are called homogeneous transformation matrices, because they transform the equations of a point which are expressed in this homogeneous coordinate system x, y, z, w. Now when we are doing robotics, we are not usually interested in points at infinity usually, but we are sometimes, so we will see why. And so it is not that people just conveniently found out that if you add that 1 at the bottom, then all these multiplications come out. So there was very strong theory which first developed that this homogeneous coordinate system, and then they said, okay, now if I have this, now what happens? Then they found out that everything works out very nicely, both rotation and translations. So that is what they were struggling with for 100 years, that you see the history of these people working on it, is simply to figure out that if I have rotations, so for translation they had figured out, by the time Newton came around they had figured it out, I can handle translations x, y, z. Then they said, okay, now if the rotation translation of a rigid body, what happens? They realized it is not commutative. So they developed all these tools to work on them, and there is much more, right? I mean, this, when did we land up? We landed up with some 1870, right, when these people passed off. So after that there is much more. So Ball did much more, and lot more has been done since then. So for that you will have to take a advanced squares course on robotics. Okay, this is not offered here, someday. Okay, so we push it more. So you have the point representation of a line, or you have the plane representation of a line. So join of 2 points, intersection of 2 planes, right. So if you look at this definition of the line, then you get these coordinates p, q, r and l, m and n. Okay. So which are again the same matrices from S1 T1, S1 U1, SV, and then similarly U1 V1. It is very similar, except that these orders are reversed, and these two orders, the LMN PQR is called the Plucker, they are called the Plucker coordinates, they are called the ray coordinate order, which is basically it's a joint of 2 points. So there is a sense of a direction which is there, and then there is axis coordinate order, in which is the intersection of 2 planes which gives you an axis. It does not give you a ray, it is not directed, and that is PQR LM and N. Okay. And finally, if the line is not an infinity, W is usually taken as 1. Okay. For the line at infinity, we said W is equal to 0. So the whole matrix becomes in this form. So for W is equal to 0, definitely LM and N are equal to 0, but PQ and R are not necessarily equal to 0. So we have a moment of a 0 force. Okay, it's an interesting concept, because we started by defining that okay, if I have a line and I take a moment, right, now we have 0 force but a finite moment. Possible? In statics? Come on, you have seen this, right? It's called a pure couple. It's not so bad, right? A couple has 0 force but a finite moment, right? But in general, if you apply a force, then about a point it will have moment and a force. So it is not so unusual. Okay. So what you can see is that what will slowly come through to is that you can have 0 force but you can have a finite moment, and that is essentially something at infinity, a line at infinity. Okay. So these are now similarly if you have that case, so if you are rotating about a line at infinity, then you get pure translation velocity, so that is like a sliding joint. Now this is something which you have already done, right, in the kinematics course. Yes, no? This you must have done. If you say no, then you should have flunked the basic kinematics course, right? If you have a rotation axis at infinity, you get a sliding joint. So this is the same representation of that. Yeah? You remember? Or don't remember? Remember, vaguely. So now one of the problems which you struggle with is that, now suppose you tell me that, so you always keep talking about force and a moment about a point. Force and moment about a point. So you talk about a pair. Now if you write it in the form of a screw, then you get a unique description. Doesn't matter which point you are referring to, it is unique in the coordinate system which is used. So we look at that. So if you have an axis at A and then the axis is going in the z direction, and you have a force N acting in the z direction, so the force is coming out of the plane, then this has, what is the moment about the x axis? It will be this into x, moment about the y axis will be this into x, and moment about the x axis will be force into that y, okay, and moment about the z axis is 0. Okay. So this gives you interesting relationships about in statics. Now similarly, identically, if you have a body which is rotating with angular velocity omega about a point A, and you take a point D which is instantaneously coincident with the origin of the coordinate system. Now since this is rotating, there is no point D which always stays at the origin here, there is a point here which stays here, that is acceptable. So point which is instantaneously coincident with the origin will keep changing, but I take the point D which is instantaneously there. So the velocity of D is omega cross AD, okay, and the, let me just, so the x component is omega ya, y component is omega xa, and the z component of that is 0. So these are identical relationships which hold. So we now extend to a slightly bigger thing. Now we have the general line in space, LMN PQR, and we have a body rotating about it. Now this body, if I look in the extended sense, it obviously, if you are familiar with this, that this can extend it and curl around this, and we will have a point on this body which is coincident with the origin. Not a very big stretch, right? You can just imagine if I just draw this like this, it will just clutter up the picture, but it will get me there. So if I have a omega about this, then the velocity components about a point which is coincident with the origin will have components p, q and r. Okay. And the velocity at any general point x, y, z is p minus this, q minus this, and r minus this matrix. Okay. You should just try proving this. It's not very difficult. It's a little bit of homework. Okay. So PQR is for a point which is incidentally coincident with the origin. If you take a general point, then you get this. You have to add something more to it. Okay, this you should be able to prove this very simply. Okay, clear? So now let's look at other nice properties. Obviously, two lines are parallel if L is to M is to N is the same between the two lines. Okay, and two lines are perpendicular to each other. They need not intersect, but they're perpendicular to each other if L1 L2 plus M1 M2 plus N1 N2 is equal to 0. Okay, very simple. Dot product is equal to 0. For two lines to intersect, okay, so essentially it means that they have zero mutual moment. That means if you apply a force about one and it's free to rotate about the other point, then you get a zero moment. So then you get L1P2 plus M1Q2 plus N1R2 plus so L M N P Q R of the first, and then you write P Q R and then L M N of the second, okay, is equal to 0. So you write one in ray order and you write the other in the axis order and take the dot product and you get this equal to 0. Okay, so this is the zero mutual moment condition. Now if you note carefully, this condition, zero mutual moment, is satisfied by two parallel lines also. Yes, no? If two lines are parallel, so L is to M is to N is the same, then essentially you know that P2 Q2 R2 is perpendicular to, and so it's also perpendicular to L1 M1 N1. So this dot product L1 P2 plus M1 Q2 plus N1 R2 is equal to 0, and then this one is also equal to 0. Now this is interesting, right? That means two parallel lines have zero mutual moment, which means they intersect at infinity. Okay. Now this was not known to human beings until the 17th century, until the 18th century. So before the 18th century, they said parallel lines never meet, right? And then suddenly they started saying no, they meet at infinity. Because see, before this, without this theory, you cannot even, so you can say that they meet at infinity, but you can never show that they meet at infinity, because moment you make x or y infinity, the equation becomes unmanageable. But in this system, essentially what you can do is you don't need to make any of them infinity, you just make w equal to 0, so you just drop out one set of terms. So you can actually deal with the line at infinity, and then you can show that parallel lines actually intersect at infinity. And what is the angle in a triangle? Sum of angles in a triangle? Who said that? You proved it. Come on, why are you guys so defensive? You proved it, right? Has it been proved? Huh? Yeah, it's Euclid's proof, right? But then there are other space, right? So, and what is the straight line? Line joining 2 points. So I have a point here, if I just join it like this, then will I get a straight line? Take the shortest distance, right? So if I have a surface of a sphere and I take 2 points and shortest line will be a geodesic, right? That you must have done in geography, right? Great circle. So I take 3 points, so I draw a great circle here, I draw a great circle here, I draw a great circle here. So there are 3 short lines. So I get a triangle. What is the angle in this triangle? Greater than 180. Can you have a triangle which is less than 180? Hyperboloid, right? Lobachevsky. Right? So, lots of fun. So, many of the things which you learn in Euclid are slightly modified, as you go along, slowly down the line. So, and then you have, so this is where the two things, the ray and axis orders, they come together, and statics and kinematics kind of join together. And so you have this very definition that the force F can do no work on a body, free only to rotate about an axis at line 1, when the line of action of the force, line 2, intersects the axis of rotation. Okay, so this gives you the condition for the work done being equal to 0. Okay, and most of your dynamics is derived on the basis of this. Okay, so you cannot derive dynamics simply from first principles. Geometry you can. Dynamics you cannot. You always need an assumption when you do dynamics. You either say, okay, I minimize the energy, or you say I minimize the path travelled or the time travelled, and that's how you get your dynamics equation. Okay. So this is essentially where the things originate, and so obviously in this you can interchange line 1 and line 2. I mean, body free to rotate about line 2, and then line 1 you get back the same definition, and this is mathematically the zero mutual moment expression statement which is there. We now look at this issue of normalization. So very simply, you divide all coordinates by square root of L square plus M square plus N square raised to the power half. So you make this one, so depending on the distance, p square plus q square plus r square has a value. Now, but if L and M n all are 0, then you divide the coordinates by p square plus q square plus r square raised to the power half. Okay. Now, angle alpha between two normalized lines, not general lines, so you normalize it first. So cos alpha is given by L1 N2 plus M1 M2 plus N1 N2, and then sin alpha is given by this expression. Now there is to square root, I just take the positive value of this. Okay, I always take the positive value, not the negative value of the square root. And the perpendicular distance between two lines is minus L1 P2 plus M1 Q2 by sin alpha, and when the lines intersect, this perpendicular distance goes to 0. Okay. So this is the normalization procedure for the line equation. And finally, we will get to this, and we will push on this more in tomorrow's lecture, is screws. Okay. So we will deal with screws, motors and wrenches, which you cannot find in a hardware store. Okay. So we will define new kind of, so we already seen new kind of screws, right? Mathematical screws, 6 things put together. So the definition is that you take a line Now line is essentially, we said, is 4 parameters, right? 4 parameters linked with quadratic identity and the fact that only the ratios are important. So then you attach a scalar pitch parameter h of dimension length. Okay. So if you do that, then you are left with infinite 5 screws in space and 1 infinity of screws on a given line, okay, because that parameter h can take any value 0, positive, negative or infinite. Okay, so that is all you are doing. So you take a line and it is okay, I just assign another parameter to it, okay, of dimension length. So we are still not talking about the geometry which comes out of it, right, because I said a line is LMN PQR with quadratic identity and the fact that there are ratios. If I normalize it, then the ratio thing is anyway gone, okay, that defines another thing with the quadratic identity. Now with that, I said if I tag on another parameter h, I get what is called a screw, okay. So I am leaving the definition vague and open like this, and it is just a mathematical definition in terms of number of parameters. So we will take it forward based on this. So in tomorrow's lecture we will find out how it matters and how using this, just this single parameter h, we can define both motion in 3D and the force movement system in 3D uniquely using this parameter and what are its properties. And the whole idea is that we are going to derive the Jacobian of a big manipulator, okay, not the little one which you have gotten in the assignment, which you people have still not solved so far, okay. Alright, so we will stop here today.